When it comes to the applications of vectors to the real world, you're usually dealing with more than one. And we try to find a resultant vector when I have two vectors or even more that are acting upon one another. And in this video, we're going to go through how to do vector operations and finding a resultant vector. We're going to start graphically. And so I'm looking at this first vector, that's vector 3, 2, and I have the vector x, that's negative 4 by 3. And remember, that's the component form for each individual vector. And I have some operations here that we want to do. So I want to find vectors that are the opposite of both u and x to begin with. Well, an opposite vector points in the opposite direction. So the opposite of u, if u was 3, negative 2, the opposite of u is going to be the vector I negate both terms. So it goes the exact opposite direction. So it'd go left 3, down 2, and there is the vector pointing in the opposite of u. The vector pointing in the opposite of x, well, x was negative 4, 3, so the opposite of x, I'm going to change both the signs, would be positive 4, negative 3. So it'd go right 4, down 3, and I'd go from the origin to that one, and I'd see the opposite of x. Now basically, the opposite of x is just negative x, and the opposite of u would be illustrated with negative u. Now let's apply the two vectors to one another. So I want to take vector u and I want to add vector x to it. I got to zoom out so I can see vector u. So u is the vector 3 by 2. And v is the vector negative 4, 3. Or not v, x. All right, so we're actually adding the two vectors together. Well, the way you do is you start with the first vector here. So I want to take u, and I'm going to graph u. So it starts at the origin, go right 3 up 2. So there is vector u. And to add x to it, what you do is I connect vectors head to tail for my operations. And so from the endpoint of u, that becomes the starting point for vector x. So vector x says go left 4, up 3. Left 4, up 3. Puts me right there. And then I'm going to connect that. So I started at the end of u, and vector x took me all the way to right here. So I have vector x. I have vector u. And the resultant vector that I get from adding those together, so let r be my resultant vector, you go from where you originally started at the very beginning, and then draw this vector up to the very end after you applied your last vector. So this is vector r. And so I drew it now, and I want to write the component form. So vector r is equal to, go left 1 unit, up 5 units, negative 1, 5. Now, notice what happened there, how I can get negative 1. If I were to add the x components together of vector u and vector x, 3 plus negative 4 gives me negative 1. 2 plus 3 gives me 5. So I can write the resultant vector by adding the x's together and adding the y's together, and I see the components of my resultant vector. Being able to draw the operation is very important for when it comes to applications. Now let's look at 2 times u. All right, so 2 times vector u, remember that's just saying take vector u and add it to itself. So vector u, get back where I can see what vector u is 3 by 2. So graphically, what I'm going to do is I'm going to apply vector u. So I start at the origin, I go right 3 up 2, there's vector u once. And then I need to do it again. So I take the endpoint, and I start, and I go right 3 up to another time. And there's u a second time. So the resultant vector goes from where I originally started all the way to where I finished. So that's my resultant vector, which basically, from start to finish, I went a total of 6 units to the right, up 4 units. Well, notice the relationship in our resultant vector to 2 times u. If I take the 2, multiply it to the 3, I get 6. If I take the 2 and multiply it to 2, I get 4. All right, so it's multiplication of a vector by a scalar. One more operation would be subtraction. So let me write vectors u and x again. All right, so u is 3, 2. Vector x is negative 4, 3. All right, now I want to subtract them. Now, subtraction is a little harder to draw graphically. And so what we're going to do is we're going to think of this, instead of subtraction, is we're going to think of this as u plus the vector negative x. Well, the vector negative x means that I need to make both components, I need to change their sign. So it would be 4 by negative 3 is negative x. So that's actually what I want to apply there graphically. So I start with vector u, so write 3 up 2. All right, so I did u. And then add to it vector negative x, which says go right 4, down 3. And connect. So that's vector negative x. And my resultant vector here would go from start to finish. So from the origin to where I ended up, that's my result. So that's how we do vector subtraction. Now, the resultant vector here, it went right 7, down 1. There's a component form. Notice the relationship that if I take u and subtract the x value of the vector x, 3 minus negative 4 made 7. And 2 minus 3 made negative 1. So operations between vectors, adding and subtracting, you just add and subtract your individual x components together. All right, now let's do 2 examples. So I want to find the component form for each resultant vector here. And the resultant vector is what it wants me to find. So it wants me to find 5 times f plus 2 times b. So I would start with figuring out what negative 5f is. Well, negative 5f is going to equal negative 5 times negative 11 by negative 5 times 6, which is going to give me 55 by negative 30. And then I'm going to figure out what 2b is. Well, 2b is going to equal 2 times negative 8 and 2 times negative 4. 2b is going to be the vector negative 16 by negative 8. And then we want to add them together. So I'm going to add my x's, and I'm going to add my y's. And so my end result here would be 55 plus negative 16 by negative 30 plus negative 8. And so the final vector (29), or actually not 29, 39 by negative 38. Now let's go to another example here. Well, same thing, but now I display the problem a little differently. So we want to find 5u plus 6v, but my vectors aren't written in component form. I'm given the magnitude and the direction angle. So u in component form would be 3 times cosine of 210 by 3 times sine of 210. V here would be 9 times cosine of 338 by 9 times sine of 338. And so what it wants me to find is 5 times u plus 6 times v. So that resultant vector, if I want to do this thing all at once, would be I need to take 5, multiply it to u. So it'd be 5 times 3 cosine of 210. And add to that 6 times v. So 6 times vector v. So its x component is 9 cosine of 338. So that's going to give me the x part. And now I got to get the y component. So 5 times the y component of u plus 6 times the y component of v. And then I'd evaluate that in my calculator, making sure I stay in the right mode. And so we get an x component of 37.08. And I get a y component of negative 33.22. All right, now let's find a unit vector. All right, so I have vector u that has components of 8 and 15. I want to find a unit vector that points in the same direction. So what I need to do is I need to first find the magnitude of u. So the magnitude of u is equal to the square root of x component squared plus the y component squared. So 64 and 225, 289, which gives me 17. And so my unit vector, simply, what you're going to do is you're going to take the components of u and you're going to divide them by the magnitude. So 8 over 17 by 15 over 17. So I have my unit vector. Now, the next operation we're going to talk about is the dot product. There's actually two kinds of products between vectors. There's a dot product and a cross product. But in this video, we're only going to talk about the dot product. The dot product, when I perform it between two vectors, it yields in a scalar measure, so I get a number at the very end. And the way it works is you're going to multiply the x's together, multiply the y's together, and you're going to add them together. So we're going to perform the dot product here for this problem right here on the right. So I want to find u dot v. Well, what I'm going to do is I'm going to take the x parts and I'll multiply them together. So it'd be equal to 4 times negative 8 plus, multiply the y's together, 9 times negative 2. And then you add. Remember, you are not getting a vector answer. You are going to get a scalar. So I'm just going to get a number. And my dot product here yields negative 50. Now the dot product is useful in terms of helping us be able to find the angle in between two vectors, which is where we're going at next. Trying to find the angle in between two vectors, one option that we have is to draw the vectors out and to make triangles and to help us solve for for the angles in between them. And the angle in between the two vectors, I went ahead and graphed vector u and vector x. And the angle in between them is going to be the angle in green. So the overall angle here is the angle between. Now I'd start by finding the angle between vector u and the x-axis. So I'd use the tangent function. So tangent of theta would equal 2 over 3. And I would use inverse tangent to help me find what that angle is. So inverse tangent of 2/3 gives me 33.69. And I would do the same thing for the purple one. So I'd say tangent of theta, I'm going to make my sides positive, is equal to opposite over adjacent, 3/4. And that gives me an angle measure of 36.87. And to find the angle in between them, remember the overall angle of rotation from one side of the x-axis to the other is 180 degrees. So to find my angle in between my two vectors, so the angle between, is going to equal 180 minus each of those angles we just solved for. So 180 minus 33.69 minus 36.87 is going to give me my angle in between. So 180 minus 33.69 minus 36.87. 109. Before I can jump in and do this, let me show you where this formula comes from. And it comes from actually the law of cosine. So I'm going to draw two general vectors here. So let's say I have vector B. And then I have vector A. And their respective magnitudes are how long they are. And we want to figure out, well, okay, well, what would the angle in between them be? Call it theta. Well, in order to do this, we're going to close in this vector. And I'm going to make the vector that goes from B to A. And I'm going to say that is going to be equal to negative vector C. So basically, vector C itself is equal to vector A minus vector B. What we have here is we have a triangle. And we're going to wind up using, we're going to start by trying to find, let's write the components of vector C. So vector C in component form is equal to, I would subtract the x's, so I would do ax minus the x value of b. And I would do the same thing for the y's. So that would be my component form for vector C. Well, the magnitude of vector C, so that way I can create that triangle. So the magnitude of C, to close it in. All right, so magnitude of C is going to equal the square root of ax minus bx squared plus ay minus by squared, square rooted. Well, I'm going to go ahead, I'm going to square both sides. So if I square both sides here, what that's going to give me, so the magnitude of C squared is going to equal, and I got to multiply this thing all the way out, so bear with me. All right, so ax times ax minus 2 times ax times bx plus bx times bx plus ay times ay plus 2ay times by plus by times by. And I'm going to come in, I'm going to group some of these terms together. And I'm just going to write this in a slightly different order. So I have AX times AX, and I have plus AY times AY, minus 2 times AX BX, and then I'm going to have BX times BX, and BY times BY, plus 2AY times BY. And you'll see why I'm doing this is because AX times AX plus AY times AY that's equal to the magnitude of A squared. Because the magnitude of A is square the X component, square the Y component, add them together, take the square root. This second part here, the BX times itself plus BY times itself, that's the magnitude of B squared. And we have the other parts that are still remaining in there, so I still have minus 2AX times BX and plus 2AY times BY. Now, with these two terms here, if I group them together and pull out a negative 2, we would have magnitude of A squared plus the magnitude of B squared minus 2 times AX BX minus, or actually, minus AY BY. Now I have an error in here. It's right up here at the very beginning. Is that 2AY has to be a subtraction. So I gotta have minus, minus. That's gonna change this to a minus, sorry, and make this a plus. All right, so back on where we were. And so I can get back to this equation. So I wind up with the magnitude of A squared plus the magnitude of B squared minus 2 times, well, AX times BX plus AY times BY, that is how we do the dot product of A dot B. And so we think about where, oh my goodness, where did this even take us to? Well, what we have here is we have one side of an equation for us to keep working with. And so what we have right here is that I'm going to come over here to the right-hand side where I have some room. Is the magnitude of A squared plus the magnitude of B squared minus 2 times A dot B. All right, well, that's going to equal, let's set up law of cosines over here on the right-hand side for that triangle. So if I set up law of cosines and I use theta as my reference angle, we have opposite side would be c squared, which would be the magnitude of c. Well, we figured out c squared is all of this that we have. All right, so I'm just going to write the rest of the law of cosines formula because all of this is basically the magnitude of c squared. And so it would be adjacent side squared plus adjacent side squared minus 2 times their product. So 2 times magnitude of A times the magnitude of B times cosine of the angle. So this side here is law of cosines. Well, we can simplify that formula down. And we simplify that formula down because we're going to get things to cancel. and then I would divide by negative 2 times magnitude A, magnitude B, and we get cosine of the angle in between two vectors is equal to A dot B divided by the magnitude of A times the magnitude of B. And so here is an alternative way to find the angle in between two vectors. And so if I go to apply that to the first problem that we had, and so I don't really have a whole lot of room here to do it, but we'll try to make that work, is if I go back and we have vector u at the very top. So vector u is equal to 3 by 2. Now the magnitude of u would be equal to the square root of 3 squared plus 4 squared. So 9 plus 4, square root of 13. And then I'd go find, do the same thing for x. So vector x is equal to negative 4 by 3, which its magnitude would be 16 plus 9, square root of 25, so 5. So I got the magnitude of A, and then I got the magnitude of, magnitude of x and the magnitude of u. Now I just would need to find the dot product between the two. So u dot x. So u dot x would equal 3 times negative 4 plus 2 times 3. So negative 12 plus 6 gives me negative 6. Now according to our formula, cosine of the angle in between the two vectors should equal negative 6 divided by 5 times the root of 13. And if I do apply the inverse cosine to that, let's see what we get. So inverse cosine of negative 6 divided by 5 roots of 13. And we get, okay, so vector projection is, it talks about what is the effect that one vector has in the direction of another. And the best way for me to try to explain this to you is with a pretty basic example here. So let's say I have a car that's broken down on a road. All right, I'm just going to draw a box for the car because I'm no artist. So here's my car, and there's a driver in this car that is going to make sure that this car travels in that straight path that the road is on. And let's say I drew the short end of the stick here, and I'm the guy that's behind this car that's having to push on it. And so I'm pushing on the car. But let's say I'm not pushing in the exact direction of travel. Maybe I had I'm a little bit off to the side, and I'm kind of pushing off here at an angle. So here's my force that I'm pushing the car to make it move. Now the question we have is, well, what is the effect of my push, since I'm not pushing in the same direction as the car is, on the direction it's going? So how much of my push is actually applied in this direction? Well, this is the projection. Now, the way we would determine what the vector projection is of my force acting in the direction of travel is I'm going to start by doing a little bit of a proof, and I'm going to start with what the projection is. And so the projection of a vector, in this case, I'm going to stick with A's and B's. Now, being able to read the notation is important. The bigger letter, because you have big letters and subscripts, if I'm projecting vector B onto A is going to be the subscript here. So that's what I'm going onto. So I'm projecting vector B onto A. And I have a graph here on the left-hand side I'm going to work with. And so I have vector A drawn. All right, and I want to know to what effect or how much of the components of B are acting along A. And the way we're going to do this is I'm going to close off this figure and go from the endpoint of B. I'm going to draw a line that is down perpendicular to vector A here. And if we have these two vectors, we're going to need to know, or maybe it's going to be given, what the angle in between the two vectors is. And so what I can do is, if I look at this in terms of a right triangle, I have my magnitude of B. And this component here, which would be my projection amount, would be equal to cosine, or the magnitude of vector B, times cosine of theta. Now, what I can do from here is remember that I can rewrite cosine of theta. The angle that lies in between two vectors, cosine of theta, is equal to A times B divided by magnitude of A times the magnitude of B. So I can determine the value of cosine between the two angles by doing this. And so what we're going to do is I'm going to put that in back up here and rewrite. So the magnitude of B, this is all tying into the projection of B onto A without actually having to find the direction angle, or the angle in between the two vectors, times A dot B divided by the magnitude of A times the magnitude of B, which I can simplify that. See, the magnitude of B's are going to cancel if I multiply those together. And so that simplifies to A dot B divided by the magnitude of A. And so what this is here, this is the scalar component of vector B that acts along vector A. And so to take this scalar component and apply it in the direction of A, the next thing we would have to do is we'd have to find a unit vector that acts in the direction of A. Which that unit vector is going to be, basically, it's going to be 1 over the magnitude of A times vector A. And so that's the unit vector. Well, to get my projection of B onto A, what I'm going to do, change colors. So the projection of B onto A is going to equal the product of those two. So the projection of B onto A is going to equal A dot B divided by magnitude of A times unit vector A, which is 1 over the magnitude of A times vector A. Which, if I put all that together and I simplify, we wind up with the projection formula. The projection of B onto A is equal to the dot product of A and B divided by the magnitude of A squared times vector A. So that's where the formula comes from. And what it does is it allows you to get this projection without having to solve for the angle in between the two vectors. And so it kind of streamlines the process. And I want to do one example here, and so we'll apply it. So I want to find the projection of U onto V. So the projection of U onto V, I would need to find the dot product, U dot V. So the dot product between U and V would be 6 times negative 3 plus negative 5 times 2. So that's going to give me negative 18 plus negative 10, negative 28. So that's U dot V. And then I would need to find the magnitude of V squared. Well, the magnitude of V is going to equal, you square the x component, square the y component, take the square root. Well, if I'm squaring the magnitude, it's going to take the square root off, and so that's all I need, and so 9, I end up with 9 plus 4, I get 13. And so our projection here, I plug all this back in, is u dot v, so negative 28 over 13 times vector v. And then I just apply the 28 over 13 to each component, and we get how much it acts in that direction. So I get negative 84 over 13 by, oops, by actually positive 84, sorry, and by negative 56 over 13 is my vector projection. So that's how much of u would act in